Better than you. There we go. Are we all set? Okay. Hi, everyone. Welcome to our August seminar. I'm Nancy Briggs. I'm manager of Stat Central. And today we have speaking with us Maeve McGillycuddy, who is one of our most recent consultants to join us. And she's going to talk to us about prediction and how that works in statistics. For those of you who are just joining us for the first time, we are Stat Central, a group of consultants who provide design advice and statistical analysis advice to researchers at the UNSW. And we are tasked with helping HDR students and researchers with the statistical and quantitative aspects of their projects. So you can all come in and talk to a consultant if you have questions and want some input. And we also help particular units with more in-depth help and dedicated help. So currently we're helping School of Clinical Medicine and Bees and Kids Cancer Center. And are there any more? Did we get them all? Yes. Yeah, I think that's it. And we also provide help for bigger projects like analyzing data from grants. And you can get information about that by contacting Stat Central or our inbox, and somebody will contact you and get you the information that you need. So today, let me introduce Maeve, and she's going to talk to us now. Thank you.
Yeah, thanks, Nancy. Going to talk about prediction and just a brief introduction to it. I'm going to start off with this example. I think prediction crops up a lot in general in our lives. I think a big topic right now is who will win the FIFA Women's World Cup. So that's just out of our interest. These are predictions prior to when the game started, and it's the only first 11 or so, but I thought it was interesting, and I was hoping that when I wrote the seminar that it would be good news from last night, but unfortunately it's not. But yeah, as you can see, like here are the predictions for the first few teams. So I'm not going to try to tell you who will win the World Cup, but I will go through how do we predict. Other examples of prediction is maybe like we want to predict the success of a transplant or stock prices or the abundance of fish species. And now nowadays, maybe with the advancement of technology and techniques, we're trying to use it for diagnostic of medical images. So on the right-hand side here, it's just some images. They're trying to use machine learning to diagnose the presence of breast cancer. Or there's just the more machine learning again is image recognition. So yeah, there's plenty of like examples of where we're interested in prediction. And what is prediction? Well, prediction is just that we want to predict the response for new observation of the covariates. So here I try to put it as simply as possible. We have our covariates X and we just want to plug them in, and maybe we have some model or methods. And then what we were really interested in is we're just interested in that outcome or the response. We don't really mind what's happening behind in the machinery, but we're just mostly interested in that response. Some prediction problems is maybe choosing a subset of variables. That, like, it is more of variable selection, but we kind of approach it from a prediction point of view. So I've included there, it's kind of inference, but we kind of use prediction for that problem. Which method is best at predicting the response? For example, we might want to compare logistic regression to a classification tree and just see which one's better. Or maybe you want to tune some hyperparameters, and that's more the machine learning side of things that I'm not as familiar with, but maybe some of you out there are. Inference. So the idea is we're comparing prediction and inference. Typically we start off with a prior hypothesis, and we want to analyze some data we've collected for that hypothesis. And what we're mostly focused on is the coefficients of that model. For example, we might want to test whether or not a variable is associated with an outcome. So you might be testing whether or not that coefficient is equal to 0. Otherwise, we might be just, estimating the magnitude of the effect of a covariate. So again, the focus is mostly on the coefficients, whereas in prediction, what we were mostly interested in was the outcome. So as we saw that there are different focuses, but there is some overlap. There's some things in common. Some covariates may be used in both approaches. For example, maybe gender and age. You might end up using them in both approaches. And some methods, like we can still predict from a linear model, but how we get to that prediction is different. So there's probably more things that are different, and I've only mentioned maybe a few of them, and maybe there's a few more. Not all covariates may be used in both models, and what I mean by this is correlated covariates can be used in prediction models, but are typically not suitable for inference. So you might be aware of multicollinearity issue in inference. So there we try to avoid that, but that doesn't affect our predictions. So we don't really mind if variables are correlated when we're selecting those variables. And the assumptions we need to make, typically for inference, we have some model, and what we want to do is we want to see, well, how well this model fits, and we need to check the assumptions. So we do residual diagnostics and check, for example, linearity and equal variance, and that's an important step in inference. Whereas for prediction, it's not always the case where those assumptions need to be held. We have non-parametric methods, or methods that are kind of like a black box. We don't really check any assumptions there. Our interest in interpretation is different. Again, for inference, what we really want to do is we want to understand the relationship between, let's say, the variable and an outcome. So either that's like, estimating the size of the effect, or maybe the relationship itself. But in prediction models, again, we're not interpreting the coefficients. So it doesn't need to be interpretable. And typically, again, machine learning, plug it in. You're not sure what's going on behind the wheels, and you get their outcome. So how we approach prediction problems is different to inference, and some of that is because of the reasons I just explained in the previous slide. Prediction and inference should not be used together on the same data set. Maybe you want to check out a previous seminar by Peter, like cats and dogs, why model selection and inference just can't get along. But if inference is your main goal, there are lots of seminars held by Stat Central on this topic, so just go check out that website. Typically, models for inference may not work as well for prediction models, so that's why we kind of have a different approach for prediction. And I'm going to go through how we approach a prediction problem. So for prediction, what we want to be able to do is we want to assess a method by its prediction performance on independent test data. So ideally what we would do is, if we had lots of data, we might split it up into 3 parts. You have train, validation, and test data sets. And it does depend on the sample size, but this is in an ideal world. And I'll go into later about train and validation as well. How should we choose the number of samples in each part? Well, we're not really sure. There's no gold standard, and a classic answer is it depends. It depends on your data and the complexity. Hasty et al., which I'll show you in the next slide, recommends if you've like lots of data, 50% in the training, 25% in validation and test. Whereas some people say, well, as your N increases, your training sample size should also increase, but the proportion you assign to that training should decrease. So yeah, there's no one answer, unfortunately. I think two key things to take away from this as well is that, well, we want to randomly divide the data into those three parts. Again, that's just to reduce the bias. Maybe you collect your data in some ways similar to how you sample data. The other key thing is we want to account for any dependent structures in the data. For example, if they were temporarily sampled or spatially sampled, we want to account for that when we initially split the data set up. Otherwise, you underestimate the prediction error and your prediction will appear better. And that's like, there's a paper by Roberts et al. Going through that. So the idea there is that you want the training data set and your test data set to be independent. So that's a good way to measure the prediction accuracy on your independent test data. So what is a training data set? Well, this is just how we want to train a model or a method to that data set. And depending on your response and your data, you might want to choose different methods. I've only listed a few, there's lots more. And you can check more, like I found that paper or that book at the time to be really useful by Hasty, which I just mentioned previously. He goes through lots of different methods. For example, linear regression, GAMS, lasso, tree-based methods like classification and regression trees, neural networks, and support vector machines. So yeah, the training data set, all we're doing is we're applying our model to that data. So the important thing here is we have a validation data set, and that's used to evaluate how well we're predicting on data independent of the training data. So you can imagine that if you didn't have a validation data set, so these plots are from David's book. So if you didn't have a validation data set, what you might do is you might really want to train your model so that you get really good results for prediction, like you minimize it as much as you can, that prediction error. But what will happen is that in the out of sample data set, your predictions won't perform as well. So this is like you're overfitting your model to the data. So we consider like finding the best prediction method is a trade-off between bias and variance. Here, if you go too simple, it's biased. So yeah, your predictions are just off. Like you can clearly see it's not a linear relationship. Whereas if you overfit the data, the variance of your predictions in the out of sample will increase. So the validation data set is used to help avoid overfitting. And well, how do we measure our predictive error? Well, there's different measurements, again, depending on your outcome, your mean squared error, or maybe your misclassification error if it's binary, or the area under the receiver operating characteristic curve. So again, it's just, it depends on your outcome. It's a good idea before you start, then maybe you might pick one or two just to see how you, to measure that performance. So there are different ways of splitting the data into training and validation sets. The simplest is the holdout method. I think this is typically used when you have so much data that it might take you weeks to fit the model. I think a more common method might be K-fold cross-validation. So K is either 5 and 10 or 10, and the next slide will go through that. So there, that's for moderate sample sizes. Leave one out, cross-validation. That's useful when your sample size is smaller. So you fit the model to all samples excluding one, and you repeat that for each sample. So if you have 100 samples, then you're fitting 100 models, which is why it's preferred for smaller data sets. So this is an example of a fivefold cross-validation. We've split the data into 5 folds. We're training the model on 4 of those, and we're using the one remaining as a validation data set. And then after all of that, we can combine the results across the 5 validation samples, and then you might pick the method or the model with the best results from that. Word of caution, just sometimes, you forget things, and this is one I just came across, and I was like, oh, that's actually very important. Cross-validation must be applied to the entire sequence of modeling steps. So this is the idea that you should, like, if you remember at the start, we took out the test data set. So if you make any prior decisions, like say you want to subset even the variables you have before modeling, then you shouldn't be using that test data set in that choice. You should be applying whatever criteria you're using, like if you're doing univariate, you should apply that to the cross-validation data. So the only exception to this is if you can filter them without looking at the response, then that's okay. The test data set. This is the data set that should be set aside at the beginning of the analysis. We should only look at it once, and then this is used for the assessment of the prediction error and the final chosen model. So previously, if you have the training and validation, you might go back and retrain and rerun the measurement on your validation data sets and keep doing that. Yeah, you might overfit that way as well. So this is the idea of the test data set, is that you have an independent test data and you can measure that performance. And this is the result that you should publish. So this is a figure from a paper we read recently. It's kind of the workflow. They do use different terminology, so hopefully we can get through it. You have your entire data set, and again, we're splitting the data set up. They call the lockbox, that's what I just called the test data, and they're calling the remaining the parameter optimization set. So this is from machine learning. And then if there's any pre-processing, I think this is when you have images and you want to pre-process it. And then you can see after all of that, you can do cross-validation. So there's the training data, and then what I call the validation data set here. And then again, from this, you get your accuracy on the test data, and then you decide whether or not you think it's good enough. If not, then you can go back and modify some parameters and repeat the whole process. And then once you're happy enough, you can open the lockbox or access that test data and see how well your model does on that independent data set. So what happens if you've done all this and the tests are just not good enough, or you're not happy? Well, you should not go back and reanalyze the data. That defeats the whole purpose. Yeah, and then other methods for preventing overfitting. I mean, I didn't go into all of them. Nested cross-validation, I think you can guess what that is. There's cross-validation within cross-validation. Blind analysis, from what I can see, that's mostly used in physics. You might scramble the data labels, or some of you might add a bit of noise to the outcome, and then but you want to be able to transform it back to the original. So that's to avoid overfitting. And then there's also the pre-registration approach. So if you've a good idea of what you should be doing, you can just say, well, I'm going to decide on this and pre-register. And I think that is all.
If anyone has any questions, you can unmute yourself or type a question in the chat, and we'll make sure that that Maeve sees it. Questions?
Okay, great for me.
Thank you all for attending. We'll have another seminar in late September, and we will send out the notification shortly. Nope, I guess not.